Hello, myself Dr. Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss regarding the parallel processing. At the end of this video, the student will gain knowledge regarding how the instructions can be simultaneously executed, what is the purpose of parallel processing, how it can affect the performance of the computer, and what are various classification of computer architecture depending upon the parallel processing, and what is pipelining. So the topic learning outcome can be mapped with the course outcome of summarize the concept of pipelining and inter-process communication for advanced processor design. The topics that we'll discuss in this video are the introduction, parallel processors, Flynn classification, pipelining, examples. The parallel processing can be the one of the major feature of advanced computers. So in these, more than one task can be executed at a time by the CPU with the help of parallel processing. So nowadays, the computer architectures can support multi-programming, multi-user, and multitasking. In the multi-user operating systems, the more than one user can simultaneously work with the computer at a time. And these users can introduce the task so that more than one task can be simultaneously executed by the system. So, to support these multitasking, multi-user features of the operating system, parallel processing is the key idea behind this concept. Parallel processing is used to provide simultaneous data processing tasks for the purpose of increasing computational speed of the computer system. So, at a single unit of time, generally the computer can execute a single instruction, but with the help of this parallel processing, more than one instruction can be executed at that particular unit of time, so that the computational speed of the computer can be increased. So parallel processing systems is able to perform concurrent data processing. So simultaneous execution can be possible, which leads to concurrency of task execution. Parallel processing systems are required to meet the demand of large scale computations. The various applications where more computational incentive applications are there, those applications can has to supported by this parallel processing architecture. So these computational incentive application development demands for large scale of computational capability of the system. So these architectures must and should can support the parallel processing systems. Execution of concurrent events in the computing process to achieve faster computational speed. This is the major purpose of the parallel processing system. So, with the parallel processing, concurrent events can be executed simultaneously, which leads to achieve faster computational speed. These levels of parallel processing can be performed at job or program level, task or procedure level, inter-instruction level, intra-instruction level. So, at each and every task with multi-threading operation, the job or program level parallel processing can be achieved by this architecture. Task or procedure level with multiple program execution, the task or procedure level parallelism can be achieved. Inter-instruction level can lead to the modular programming. So, the big task of the project development can be divided into small parts. Those parts generally referred as the modules. So, inter-instruction level can be achieved with the help of modular programming. Instruction level can achieve between the between the programs of a project. The data dependency has to be eliminated with the help of intra-instruction level parallelism. So, the parallel processing can be done at task level, program level, inter-instruction level or intra-instruction level. So, what is the objective of this parallel processing? The purpose of parallel processing is to speed up the computer processing capability. So, what is it? So, this processing capacity generally refers to the term throughput. What is throughput means? The amount of instructions that are executed within a unit of time. So, the number of instructions that can be executed in a unit of time is generally referred as throughput. With the parallel processing, concurrent or simultaneous execution of tasks can be performed, so that the amount or the number of tasks that can be executed per unit of time is greatly increased, which in turn result in the increase of the throughput. So, if the throughput is increased, the response time and the performance of the system can be increased. So, to support this parallel processing, special hardware components can be needed. So, the amount of hardware increases with parallel processing, which results in the cost of the system can also be increases. So, how this parallel or concurrent execution of instruction can be achieved? With the help of the hardware. That hardware is the multifunctional units. So, parallel processing has high level of complexity. So, it can be achieved with the multiplicity of functional units. So, generally, the functional units of a computer are input unit, the CPU. CPU can again subdivided into subunits like the memory unit, next the ALU and the control unit and the output unit. These are the basic functional units of the computer architecture. So, the single ALU can has the capability of performing arithmetic as well as logical instruction processing. So, if the more than one instruction can be executed simultaneously by the computer, means the single ALU could not afford the execution of the instructions. So, multiple functional units can be installed, designed in the architecture so that it has to support the parallel processing. So, the functional unit performs identical or different operations simultaneously. So, to increase the processing data processing capability and to support more computational capability, the multiplicity of functional units can be designed in the computer architecture. So, each functional unit can perform identical or different operations simultaneously. So, parallel processing is established by distributing the data among the multiple functional units. So, the operational data can be distributed among these functional units, which results in the smooth execution of the instructions simultaneously. So, the parallel processing architectures can support the multifunctional units, then only the concurrent execution of instructions can be possible. So, a processor with multiple functional units. So, the functional unit architecture with single processing unit we discussed in the previous videos. But how the multiple functional units can be work together to achieve the parallel processing, that can be described here. So, this is the memory and this is the processor registers, and these are the various multiple functional units that are supported in the architecture of the computer. So here the adder, subtractor, separate functional unit, integer multiply can support the integer multiplication, logic unit can perform the various logic instruction execution, like and, or, exclusive or, complement, compare, all these instructions can be executed with the help of logic unit. Next, shift unit is used to perform the arithmetic shift, the circular shift, and the normal logical shift in both directions, left and right directions. Incrementer is used to increase the register or the memory content by 1. So all these are used for the integer arithmetic. For the floating point arithmetic also, special functional units can be designed. Floating point add and subtract, floating point multiply, floating point divide. So with these functional units, the multiple instructions can be executed simultaneously, which results in parallel processing. So, where these parallel processing systems are required, the major applications of these parallel processing systems are very computational incentive applications. Engineering and scientific applications can require these parallel processing systems. The expert system for artificial intelligence. So, here the expert systems are the specialized systems that can be dedicated for one particular purpose. With the help of artificial intelligence, these systems can be developed. So, seismic data analysis to analyze the data of the earthquake. So, nuclear reactor modeling and monitoring, visual image processing, VLSI design, aerodynamics, weather forecasting, genetic engineering in the defense, where computational capability is a very high demand and large volumes of data to be processed, then those application areas can generally use the parallel processing systems. How these parallel processing systems are classified based on the Flynn's classification. So, MJ Flynn classify the computer system by the number of instructions and data items that are manipulated simultaneously. So, during program execution, a program is collection of instructions. Each instruction can manipulate the data. So, a number of instructions and data items that are manipulated simultaneously. Based on these factors, Flynn classify the computer systems. There are two streams during the instruction execution. One is the instruction stream. Second one is data stream. Instruction stream means the sequence of instructions read from the memory. So, before executing the instruction can be fetched from the memory. So, the sequence of instructions that can be read from memory is referred to the instruction stream. The operations that are performed on the data is referred as the data stream. Based on these two factors, the Flynn classifies the computers as SISD, SIMD, MISD, MIMD. So, four categories can be specified by the Flynn. The classification depends on the distinction between the performance of control unit and data processing unit. So, here the first variety can be the SISD, where single instruction, single data stream computer organization is referred as SISD. The second variety is SIMD, that is single instruction stream, multiple data stream. Next, MISD, multiple instruction stream, single data stream. The fourth category is multiple instruction stream and multiple data stream. These are the four categories of parallel processing systems specified by the Flynn. Now, what is SISD systems? So, the SISD system represents a single computer containing a control unit, a processor unit, and a memory unit. So, in this architecture, a single control unit, a processor unit, and memory unit can be installed. So, instructions are executed simultaneously. Parallel processing can be achieved by means of multiple function units or by pipelining process. So, with the designing of multiple functional units like integer addition, subtraction, floating point, arithmetic, special functional units, the instructions can be executed simultaneously in case of SISD, or with the concept of pipelining, the parallel processing of instructions can be achieved. So, the maximum speed of the system is limited by the memory bandwidth. So, this memory is shared between the CPU and I/O. So, the limitation can be the instructions can be executed below the memory bandwidth. So, this is the architecture. So, here this is the data pool, processors pool, and the instruction pool. So, by using this processor, the single instruction and the single data stream can be executed. So, the parallel processing can be achieved by employing multiple functional units or with the help of the pipelining concept. So, with the multi-programming, spooling, multifunctional processors, pipelining, these the simultaneous or concurrent execution of instructions can be achieved in the SISD. The second category is SIMD. So, the SIMD is single instruction stream, multiple data stream. So, it represents an organization that include many processing units. So, multiple processing units are employed under the supervision of common control unit. So, a single control unit can monitor and control multiple processing units in case of SIMD architecture. So, all processors receives the same instruction from the control unit but operate on different data items of data. So, they can receive the single instruction but the operational buffers can be take different data items for execution of the instructions. The shared memory unit must contain multiple modules. So, the memory unit can be shared to support these operational buffers of multiple data items in SIMD architecture. So, here multiple processing unit can be employed which can receive the single instruction but the data can be, the buffers can be used multiple data items, the instruction can be executed in case of SIMD. Next one is MISD, multiple instruction, single data stream. So here the processing units can be more than one, and the multiple instructions can be received by this processing unit, but the data stream can be a single data stream. So there is no practically the parallelism can be achieved with this type of architecture. So no practical systems can be constructed with MIST. They are of less use. Next variety is MIMD, multiple instruction stream, multiple data stream. So MIMD systems capable of processing several programs at a time. So multi-programming can be supported by the MIMD architecture. Most of the multiprocessor and multitasking systems come under this category. So multitasking, multi-user, multi-programming systems can support by the MIMD architecture. So here multiple processing unit can receive multiple instructions and can be applied on multiple data stream for the execution of the instruction. So the concurrent or parallel processing can be achieved with the MIMD. So the comparison between SIMD and MIMD can be done based on few parameters. The first one is the full form. SIMD is the single instruction, multiple data, but MIMD is multiple instruction, multiple data. The second factor that can be considered is memory requirement. For SIMD, a single memory unit can serve for the execution of the data. So, SIMD can have smaller memory requirement, but MIMD can support multiple data. So, larger memory requirement can be considered in the MIMD architecture. Programming and debugging can be done synchronously, but in MIMD architecture, asynchronously, the debugging and programming can be executed. Next one is number of decoders. Here SIMD single, but here multiple. In the MIMD, multiple decoders can be employed in order to decode the multiple instructions. The cost can be SIMD is low, but MIMD is medium. Performance and complexity can be SIMD, simple architecture and moderate performance. In the MIMD, it has to support multiple instruction stream, multiple data stream. So, the performance can be efficient, but it is a complex architecture. So, these are the few parameters that can be used to differentiate the comparison of SIMD and also MIMD. So, what are the summary of these Flynn's classification? So, SISD can be the superscalar processors. So, super pipelined processors, and they can be the VLIW design of architecture. So, these are the small architectures but can achieve the parallelism with less complexity. MISD is non-existent. Practically, they are not possible. SIMD is using the parallelism, achieve the parallelism with the help of array processors, systolic arrays, associative processors. So, here the memory can be the content addressable, so that SIMD can use the associative processors and can execute the concurrent execution of the program. Next is MIMD. MIMD can use two techniques for sharing the data. That is the shared memory multiprocessors or message passing multiple computers. In the shared memory multiprocessors, bus-based architecture, crossbar switch-based, multi-stage based architectures can be used to support the shared memory multiprocessors. So a part of the memory can be dedicated to share the common variables between the multiple programs. In case of MIMD, shared memory multiprocessor architecture. In case of message passing, the kernel or the control unit can take care the communication in inter-process communication and inter-process synchronization mechanism. So here the internal structures can support hypercube, mesh, reconfigurable architectures can be used in the message passing multi-computers. So how the hierarchical nesting of these classification processes can be placed. So MIMD is the top priority one, which is used for parallel processing, and the instructions can be executed more efficiently. So optimized performance can be achieved, and it can be achieved with the help of multiple data structures. The second preferred architecture is MISD. So parallel computing of data and relation to CPU and the SPU can be done with the help of MISD architecture. Next, SIMD architecture, instruction execution can be done with a CAT fashion, and operational buffers inside the SPU can be used to support the multiple data stream. Next architecture is SISD. So instruction execution can use the B plus trees so that the storage of data can be effectively managed, and dynamic allocation and retrieval of data stream can be possible with multiple operational buffers. So these are the hierarchical nesting of the parallel processors. What are the domain preferences for these parallel processors? So depending upon various domains, for the transaction processing applications, SIMD can be preferred. Why? Because it can be used for sequential processing of the transactions. For the face recognition applications, MIMD can be preferred, which can be a combination of shared memory as well as message passing techniques. For the 3D graphic rendering, SIMD can be used with the help of shared memory architecture. For the patterns and search, the SIMD can be used. So here data processing can be done with the help of multiple processing levels. Next, for the radar applications, MISD as well as MIMD architectures can be preferred. That is the which can support the message passing techniques. Database queries, the data processing, data parallelism can be achieved with the help of SIMD architecture. So depending upon the application domain, the architectures can be preferred. So parallelism or concurrent execution of the instruction can be achieved with one special technique called the pipelining. Now, what is pipelining? So pipelining process is an implementation technique where arithmetic sub operations or the phases of the computer instruction cycle overlap in execution. So two or more instructions can be parallelly executed in the parallel processing architecture. When one instruction has to be executed at one stage of instruction, the next instruction can start execution, so which can lead to the overlapping execution of the instructions. So the instructions can be segregated as their parts. Those can be referred as segment. If first instruction in the first segment, after completion of this, it can move to the segment 2 of the first instruction. There, during that time slot only, the first segment of the second instruction can commence. So, the pipelining can support overlap in instruction execution. So it is a technique of decomposing a sequential process into various sub-operations. So each sub-process being executed in a special dedicated segment and can operate concurrently with all other segments. So each separate instruction has to be executed and can be overlapped with other instruction segment for the execution. So a pipeline can be visualized as a collection of processing segments through which binary information can flow. So a way of spreading up execution of instructions is referred as pipelining. So overlap execution of multiple instructions can be supported with the concept of pipelining. What is the key idea of the pipelining? So break big computational task into the pieces. Separate each piece with a pipeline register. So it is faster for repeated computations. Pipelining increases throughput. So more than multiple instructions has to be executed in a single unit of time, which can lead to increase of the throughput with the concept of pipelining. So here the computational task can be broken into small pieces, and each piece has to be stored and processed with the help of the pipeline registers, and this concept can be preferred for repeated computations. Consider one example to illustrate the pipelining concept. Suppose we need to perform multiply and add operations with a stream of numbers. For example, I is 1, 2, 3 until 7 repetitions it must be required, and the processing task can be A into B plus C. So multiplication operation associated with the addition operation. So here the computational task can be divided into small pieces with the concept of pipelining. So each sub instruction is implemented in a segment within the pipeline. So each segment has 1 or 2 registers and a combinational circuit for store and processing of this segmented data. So the sub operations performed in each segment in this operation can be divided into first input A register and the B register. So these values can be moved to the R1 register and R2 register respectively. In the second segment, multiply and input the C. That is, R1 value and R2 value can be multiplied and the result can be moved to the register R3. At the same time, the C can be inputted to the register R4. The third segment is add C to the product. The product is stored in the register R3 and C is input to the register R4. So R3 plus R4 can be added and the result is stored in the R5. So this computational task can be divided into 3 segments. This is the segment 1. And in the segment 1, the input for the AB can be stored in the corresponding registers of R1 and R2. In the segment 2, the multiplication of R1, R2 can be performed. Simultaneously, the C input can be loaded to the register R4. In the segment 3, the product can be added to the C input, which can result in the final result and can be stored in the register R5. So this computational task can be divided into 3 segments. So how this process can be achieved? During the first step, A value can be moved to the register R1, B value can be moved to the register R2. So this is the segment 1. And in the second segment, the multiplication can be performed and at the same time C value can be moved to the register R4. So here R1, R2 can be multiplied with the help of multiplier circuit, and the result is stored in the R3. Here A multiplied B value can be stored in the R3 and C is stored in the R4. So this is the segment 2. And at the segment 3, this multiplied value and the C input can be added and stored in the register R5. This is the addition operation, that is the segment 3 operation. So the computational task of A into B plus C can be divided into 3 segments. So how the pipelining process can be carried out? So during the first clock tick, so each and every processor activities can be initiated and controlled by the clock pulses that are generated by the sequence counter of the control unit. During first clock pulse, the segment 1 operation can be performed so that A can be stored to R1, B can be stored to the R2. And second clock pulse, the second iteration of A value and B value can be stored to the corresponding registers of R1 and R2, and first instruction moved to the segment 2 execution. This is the segment 1 of the first instruction. So here this is the segment 1 of the second instruction. So here the segment 1 of the first instruction moved to the segment 2. So here the multiplication of A1, B1 can be done and C1 can be inputted to the register R1. But at the same time, parallelly, the second values of A2, B2 can be moved to the R1 and R2. The first segment of the second instruction can be executed. So parallelism can be done here. And in the third clock pulse, the third values of A, B are loaded to the R1 and R2 segment 1. So this is the segment 1 of the third instruction. And here the second instruction moved to the segment 2 where multiplication and also the C2 input can be done. So this is the segment 2 of the second instruction. The first instruction moved to the segment 3 operation where the multiplication value result and the C input can be added. This is the S3 of the first instruction. So that in the 3 clock pulses, the first instruction execution can be completed. And second instruction is at the stage of segment 2. Third instruction is at the stage of segment 1. Like this, concurrently, the instructions can be executed in case of parallel processing. So this relationship can be pictorially illustrated with the help of time-space diagram. So here how the segment has to be executed and how the instructions can be traversed with the clock pulses can be pictorially illustrated with the space-time diagram. So in this way, the pipelining can be used to achieve the concurrent execution of the instructions. So it first divides the computational task into segments so that one instruction is at segment 1 and it is moved to segment 2. During that time, the second instruction can be loaded and can be executed. So this is about how the parallel processing can be achieved. What is parallel processing? How it can affect the performance? What are the Flynn's classification? And what are the major features of this classification? How parallel processing can be achieved with the concept of pipelining. And these are the references that can be used in this video. So, thank you.
Like, share and subscribe. Hit the bell icon for more updates.